Hello and welcome to this episode of SPSS one-on-one series with Word Analytics. Today we look at how to interpret results of a factor analysis in SPSS and how to report the results of your research output. We are using a fictitious dataset which you can access through a link in the description of this video and download for your practice. Here we have 10 items or variables, and we want to see what is the underlying structure. What are the groups that can be extracted from these 10 variables? So we are going to use factor analysis. To do a factor analysis, simply go to Analyze, Dimension Reduction, and click on Factor. Then we are going to push in all our factors, 10 of them, into the variables box. Under Descriptives, click on Coefficients, Significance Levels, Determinant, and the KMO and Bartlett's test of severity. Continue. Then under Extraction, we are going to use Principal Axis Factoring. We explained these different types in our previous episodes. The link is in the description of this video. Click Continue. And under Rotation, we are going to use oblique methods because our research question is aimed at just establishing the underlying structure. We don't intend to use our factors for further analysis. Otherwise, we would have used the orthogonal methods. Just like I said, all this has been explained in our previous episode. Check it out. We are going to use direct oblimin. Click Continue. And then under Options, we are going to select Sort by Size and suppress small coefficients. And we want coefficients above 0.3. They are the ones that shows that there is a relationship amongst our variables. So click Continue and then click OK. So in our output, we have a correlation matrix here. We have the KMO test and the Bartlett's test. We have communalities. We have total variance explained by the eigenvalues. We have the factor matrix and pattern matrix, but we interpret the pattern matrix and the factor correlation. In our output, the KMO and the Bartlett's test indicates the suitability of your data for factor analysis. You're interested in values close to 1. But in practice, values of 0.6 and above are considered adequate. What the KMO test is simply telling you is that there is enough variance in your data that it can be partitioned by factor analysis. Then we have the Bartlett's test of severity, which checks if your correlation matrix is significantly different from any identity matrix. And if this test is significant, it indicates that factor analysis is appropriate. Next, we have the correlation matrix. And this correlation matrix, we are interested in values above 0.3. Remember, in factor analysis, we want to extract groups of variables that are related. So we need to first run a correlation matrix to see whether there is even a relationship among the variables we are putting together in factor analysis. And here we can see several of them have correlation coefficients above 0.3, indicating that the variables are related. So high correlation suggests that the items may share underlying factors. So we are most likely able to extract factors. We have a table for communalities in our SPSS output, and communalities represent the proportion of each variable's variance that factors, the extracted factors, can explain. Higher communalities indicate that a large proportion of the variable's variance is accounted for by the extracted factors, which is essential for reliable factor analysis. When you look at initially here, the communalities show variance accounted for by the initial solution. But subsequently, extraction communalities show the variance accounted by the retained factors. providing a clear picture of the factor's effectiveness. We have here a table for total variance explained. This table provides eigenvalues and the percentage of variance explained by each factor, which is vital for determining factor significance. Factors with eigenvalues greater than 1 are typically retained, ensuring that only meaningful factors are considered. You see that factor 1 with eigenvalue of 4 accounts for 45.429% of the variation in our data, and factor 2 with eigenvalue of 3 accounts for 32.013%. So both factors cumulatively account for 77.442% of the variation. Here we have a Scree plot which can also be used to determine the number of factors that you should extract. And here it shows you that we have only 2 factors above 1. We have these with the eigenvalue of about 3 point something and the one of 4 point something. So these are the only 2 factors that can be extracted. So it is a graphical representation of eigenvalues associated with each factor, and helps determine the number of factors to retain using the elbow point, the point of inflection where the eigenvalues become flat. So with this, other books recommend that at this point you can determine that you can extract 3 factors, but based on eigenvalues we can only extract 2 factors. Here we have a factor matrix that shows factor loadings of each variable before rotation. Factor loadings indicate the correlation between the variable and the factor that has been extracted. But SPSS also provides you with a pattern matrix after the rotation, and the method is even here. You have used Oblimin with the Kaiser normalization. This rotated component matrix displayed the factor loadings after rotation, making the factor structure easier to interpret. So based on these findings, we can see that item 1, 2, 3, and 4, these 4 items load together, and then these 6 items also load together on factor 1. Please note that all those empty cells we are seeing have got values in them, but because we suppressed correlation coefficients below 0.3, they are not displayed. They have values, but the correlation coefficients are all below 0.3. Note that if you run your analysis and you find that an item or a question loads on more than one factor with a correlation coefficient above 0.3, consider that variable under a factor where it loads with the highest correlation coefficient. And here we are interested in the magnitude of the correlation coefficient, not the sign. So questions 1 to 4 are used to explain a particular factor. There is that underlying structure in your data explained by the first 4 questions. All the people that you interviewed, all the 500, the way in which they answered those 4 questions was in some way related. So they were grouped together. Then factor 5, 6, 7, 8, 9, and 10, the way people answered them were also related, the 500 people, and they were also grouped together. So using these questions, you can now come up with the names of the factors. In our previous episode, we saw that these 10 items had actually names. One is trust in team support, communication quality, and shared goals. Then when you see these 4, they are all about team dynamics. So in your data, you are able to establish that there is a construct of team dynamics in my data set. which is factor 1. And then when you look at job satisfaction, life balance, motivation, stress levels, workload, and burnout, they also form a construct that you can give a name of, say, job satisfaction. The name given to this depends on the items or the variables constituting that factor, and it is you to give the most appropriate name. So based on our analysis, we are able to come up with the factor 1 and factor 2, and we give them names. So next we see how could we report the results of our analysis. So this is how we would report the results of our analysis, and in fact this is basically factor analysis, because that's the method we used for extraction, the common factor analysis or the principal axis factoring in SPSS. In our next episode, we look at a scenario where our goal was to reduce this data into factors that we can use now for further analysis in multiple linear regression or any other analysis. If you find this video useful, consider liking and subscribing to the channel. I would greatly appreciate. See you in the next video.